In this video, we're going to think about ideal gases. We are going to think about how a gas behaves, what it does, how it works, and how we can identify and calculate different information. So as we think about how gases behave, one of the things that really led to this was that there were scientists, Boyles, Charles, and Avogadro, who studied the relationship of different gases. And so they looked at gases under different conditions, varying different things. And so as we look at these three, they varied the relationship between pressure, which is P, volume, which is V, temperature, T, and the one that is probably the most interesting is the quantity of gases in terms of moles, which is N. So they're going to look at the relationship between how a gas behaves when we vary things like pressure, volume, temperature, and quantity of gases, mole N. And these three scientists lay the foundation for what becomes the ideal gas law. So the first one is Boyles' law. Robert Boyle investigated the relationship between pressure and volume. Together with Robert Hooke, they observed an inverse relationship, which means as the volume increases, the pressure decreases, or as the volume decreases, the pressure increases. So if we have two containers with a movable piston, and those two containers are of similar volume, if on the first one, hold on, we're going to erase this line here because we don't need it. And so let me redraw this. If in this case we have a gas inside the container under volume 1 or at half volume, so the pressure is greater when the volume is decreased. And so this sign here means proportional. And so this says that the volume is proportional to the inverse of the pressure, or that volume times pressure is equal to a constant. And so one of the things that if volumes times pressure is a constant, if you have constant temperature and moles, so constant T and N, for a same condition, the pressure times volume for one system is equal to the pressure times volume for the second one. So P1 V1 equals P2 V2, where we look at the pressure under different conditions. So an example is we have a scuba diver that takes a 2.3 liter balloon from the surface of the ocean or lake, where the pressure is 0.98 atmospheres, to 25 meters below the surface, where the pressure is now 3.1 atmospheres. What is the volume of the balloon at 25 meters? So we're going to look at the relationship between P1 V1 equals P2 V2. And in this case, I'm going to make 2 red. And so in this case, the 3.1 atmospheres is the pressure. And P1 is going to be blue, where we have 0.98 atmospheres and 2.3 liter balloon. By color coding these, I'm going to have the ability to make sure that I use the right systems together. So this calculation is 2.3 liters multiplied by 0.98 atmospheres. And that's actually equal to 3.1 atmospheres multiplied by V2. So we can solve for V2, which is equal to 2.3 liters multiplied by 0.98 atmospheres divided by 3.1 atmospheres. So the atmosphere units will cancel, and V2 is going to be equal to 0.73 liters. So we can see that as the pressure increased, the volume decreased. And so we can look at this relationship for any given system. So let's think about Charles's law. Charles, or JAC Charles, studies the relationship between volume and temperature. We know that many substances contract when the temperature is lowered, such as metals get a little bit smaller. We know that gases contract. And so one thing they looked at is if you have a balloon and it gets hot, your balloon is going to get much bigger. And if it gets cold, your balloon is going to get much smaller. And this is proportional to temperature. And so this suggests that volume divided by temperature is equal to a constant. So as Charles continued to study the relationship between volume and temperature, he started to plot these two values on a graph. What he noticed was that as we changed volume and temperature, or changed the temperature for a system and measured the volume, it created a linear line that you can see in this graph. One of the things that he realized was that if you extrapolate backwards, what you're going to start to see is that there is a temperature at which the volume is predicted to be zero. So that temperature is right here, and that is absolute zero, or 0 Kelvin. And so the absolute zero, which is the temperature at which the volume is zero, or predicted to be zero, it has yet to be observed, but what we know is that that is what the expected calculation is. So Charles's law looked at this. Similarly to Boyles' law, they noted that we can vary the volume and the temperature as long as the pressure and the quantity are constant, that V1 divided by T1 is equal to V2 divided by T2. So in this example, we have an expandable cylinder and it has an initial volume of 88.2 milliliters at 35 degrees Celsius. If the air in the cylinder is heated to 182 degrees Celsius, what is the final volume of the air in liters? One of the things we need to remember is that all of the gas laws are conducted in Kelvin. This is what Charles's law determined when he plotted the relationship between those two. He used a different system, which it comes from Lord Kelvin, which is a different scientist. So we are going to make sure that we calculate all of our temperatures for gas laws in Kelvin. So in this case, I'm going to decide that 2 is blue and situation 1 is red. So if we have an initial volume, that makes this volume 1 and temperature 1, and we have temperature 2 as 182. So the first thing we need to think about is how do we convert temperatures back to Kelvin? So T1 is 35 degrees Celsius. We're going to add 273.15, and this gives us 308.2 Kelvin. For T2, we're going to take our 182 plus 273.15, and that's going to give us 455 Kelvin. So from here, we're going to plug these values into our calculation of 88.2 milliliters divided by 308.2 Kelvin, and that equals V2 divided by 455 Kelvin. And so V2 is equal to 130 milliliters. And so we can now look at the relationship between volume and temperature. So our next scientist is Avogadro. We met Avogadro in previous videos. This scientist determined how many atoms or substances are in a mole. So in this case, he's going to study the relationship between volume and moles. We know that if you have 2 cookies, it takes up more space than 1 cookie. The same is going to be held true in gases, that volume is directly proportional to moles. So V over N is going to be equal to a constant. So Avogadro's law states that the volume divided by moles in one situation is equal to the volume divided by moles in the other situation, where volume is in liters and moles is in moles. So if a chemical reaction produces 0.621 moles in a container with a movable piston, if the reaction starts with 0.120 moles of a gas and a volume of 2.18 liters, what is the final volume? Now in this case, we have V1 over N1 equals V2 over N2. And I'm going to color, this is 2 and this is 1. So that 0.621 moles is our final volume, or our final moles, and we start with 0.120 and 2.18 liters. So in this case, we're going to have 2.18 liters divided by 0.120 moles, and that gives you V2 divided by 0.621 moles. So at the end of this calculation, V2 is 11.3 liters. And so it's important to note in this calculation that we could solve for this, but I also want to talk about what the word movable piston means. So in order for the pressure to be constant, we need the ability for this container, for the top of this container to be able to move up or down based on the volume of the system. So it's freely moving and it moves up and down. And so that's what's called a movable piston. In a different situation where the volume was constant, this lid here would be unmovable, and so pressure would increase or decrease based on the environment. So when we look at all of these, we can start to ask ourselves, what does all of this tell us about gases? So together, where we know that volume is proportional to pressure, or is proportional to the inverse of pressure, the volume is proportional to temperature and proportional to moles. So we can start to think about these as saying pressure times volume equals a constant. Volume over temperature equals a constant. Volume over N equals a constant. So we can start to adapt these to where pressure times volume divided by temperature times moles is equal to a constant, where this constant is going to be equal to R, the ideal gas constant. So more commonly, this equation is written PV equals nRT, and this is the ideal gas law. So PV equals nRT, and there are multiple different values for the ideal gas constant. And so you can see those in this table on the right. The one that we will use the most often is this one here. And so this just happens to be the one that I have memorized. But when we look at this, you can see that we can change joules and calories, which we will talk about in a later series, or use different units. So the ideal gas law is going to allow us to calculate the behavior, provided we know 3 of the 4 values: pressure, volume, moles, temperature, in Kelvin. What we'll see later is that this law is only valid under certain conditions. And so this does have some complications, but overwhelmingly the ideal gas law is applicable to most situations. So calculate the volume of a gas that contains 0.845 moles of nitrogen gas at 1.37 atmospheres and 42.0 Celsius. So in this case, we're going to use PV equals nRT. And so we know that because it's a gas, but the other way we could have figured that out is by writing down what we know. We know that N equals 0.845 moles, and P equals 1.37 atmospheres, and T equals 42.0 degrees Celsius plus 273.15 is going to be equal to 315.2 Kelvin. So we are also looking for volume, and that equals question mark. So now we can rearrange this equation to be V equals nRT over P. And so we have N, P, T, and R, so we can solve for the volume. So the volume is N, which is 0.845 moles, multiplied by the R value of 0.08206 liters, atmospheres, mole, Kelvin, multiplied by the temperature of 315.2 Kelvin. I'm going to divide that by the pressure, which is 1.37 atmospheres. So when we cancel out our units, we can see that the moles cancel, the Kelvin cancel, the atmospheres cancel. That's going to give our final answer in liters. So the volume in this case is equal to 15.9 liters. So as a second example, calcium carbonate, which is CaCO3 solid, is the principal compound in limestone. It decomposes upon heating to calcium oxide solid plus CO2. A sample of calcium carbonate is decomposed and the carbon dioxide is collected in a 250 ml flask. After decomposition is complete, the gas has a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. How many moles of CO2 gas were generated? So we could write a balanced chemical equation of calcium carbonate, solid, decomposes into calcium oxide, solid, plus CO2, gas. So in this case, we can now ask this question. So it's asking for moles, which is N, and that equals question mark. We have a volume of 250 mils, which is equal to 0.25 liters. We have a pressure of 1.3 atmospheres. And we have a temperature of 31 degrees Celsius plus 273.15, and that equals 304. So now we can rearrange PV equals nRT to be N equals PV over RT. So we can just plug that in, where the pressure of 1.3 atmospheres is multiplied by the volume of 0.25 liters, divided by the R value of 0.08206 liters, atmospheres, mole, Kelvin, multiplied by the temperature of 304 Kelvin. Put that back in here. So then we can actually go ahead and cancel out our units. So the reason we converted to liters is so that it would cancel. And so that's going to give us with a final unit of moles where N equals 0.013 moles of CO2. So as we start to think about this information, the question we have to ask ourselves is, how does this work? Can we also use this calculation to start to think about balanced chemical equations? So if we want to use the ideal gas law, we can also use it in terms of an equation. So if we start to look at this information, we could start to ask ourselves, what about a balanced chemical equation? So let's think practically. Automobile airbags are inflated by the nitrogen gas generated by the decomposition of sodium azide, which is NaN3. So when it decomposes, you get 2 moles of sodium plus 3 moles of nitrogen gas. If an airbag has a volume of 36 liters and is to be filled with nitrogen gas at 1.15 atmospheres and 26 degrees Celsius, how many grams of sodium azide must be decomposed? In this calculation, when we set up PV equals nRT, N is going to be the moles of nitrogen gas. And then we can use traditional balanced chemical equation to convert from moles of N2 to grams of NaN3. So let's set this up. So we know that the pressure is equal to 1.15 atmospheres. The temperature is equal to 26 plus 273.15, and that's going to give us 299 Kelvin. We know that the volume is equal to 36 liters. So with this information, we can solve for N, where N is equal to PV over RT. So first, we're going to take our 1.15 atmospheres, multiply that by the 36 liters, divide by 0.08206 liters, atmospheres, mole, Kelvin. And then multiply that by the temperature of 299 Kelvin. So when we cancel out our units, we're going to be left with N is equal to 1.69 moles of nitrogen gas. Once we have the moles of nitrogen gas, we can start to think about how could we convert that back to the grams of sodium azide. This goes back to the balanced chemical equations where we can go from grams to moles to grams in terms of something starting with solid or using molarity in previous videos. So we're going to take our 1.69 moles of nitrogen. For every 3 moles of nitrogen, we need 2 moles of sodium azide. And 1 mole of sodium azide is equal to 65.00 grams of sodium azide. And once you plug that in, you're going to get 73 grams of NaN3. So for every 73 grams, you're going to be able to produce or completely fill a airbag if it is 36 liters at 1.15 atmospheres and 26 degrees Celsius. So we can start to also think about this in other examples. So methanol can be synthesized from carbon monoxide and hydrogen gas using this balanced equation. So what volume in liters of hydrogen gas would be required to synthesize 35.7 grams of methanol using the following balanced equation at 82 degrees Celsius and 738 millimeters of mercury? So we are provided the mass of methanol. So we're going to have to go from methanol to moles of H2. Then we'll use PV equals nRT to solve for the volume of H2. So in this case, we're going to start by converting grams to moles and then use our balanced chemical equation. So we're going to take our 35.7 grams of CH3OH, divide by the molar mass of 32.05 grams and 1 mole. We're going to use this balanced chemical equation of 1 mole of methanol for every 2 moles of H2. And so that gives us 2.23 moles of H2. And this is going to equal N. So we know that the temperature is 82.0 degrees Celsius plus 273.15, and that's going to give us 355.2 Kelvin. And then we also know that our pressure is equal to 738 millimeters of mercury. We're going to divide that by 760 in 1 atmosphere. And that gives us 0.971 atmospheres. From here, we are going to go ahead and plug this into our calculation, where the volume is equal to nRT over P, where the N is 2.23 moles, multiplied by 0.08206 liters, atmospheres, mole, Kelvin, multiply that by 355.2 Kelvin, divide that by the pressure of 0.971 atmospheres. Oops, need to move that a little bit further. So the last thing, once we plug this all into our calculator, is that we're going to get that the volume is 66.9 liters. So the important things to remember are to make sure that you use both the balanced chemical equation and the PV equals nRT. So let's look at another example. So octane is combusted in a combustion engine. The products are carbon dioxide and water. So we have a balanced chemical equation. In the gas tank for a Dodge Neon, it contains 12.0 gallons of gas, which contains 0.821 kilograms of octane. If the car is driven on a cool day, which is 18.2 degrees Celsius with a pressure of 0.928 atmospheres, what is the volume of carbon dioxide that is produced? So we are looking for N of CO2. We know that the temperature is 18.2 degrees Celsius plus 273.15, and that gives me 291.4 Kelvin. We know that the pressure is equal to 0.928 atmospheres, and we are looking for the volume. Now, you might think, we know it's 12 gallons of gas, but that's the volume of the gas tank. We're asking about what is the volume of CO2 that is produced. So let's figure out the moles of CO2 by converting the grams of octane into moles of carbon dioxide. So I'm going to take my 0.821 kilograms, multiply by 1,000. Then I'm going to take my 821 grams of octane, divide by 114.26 grams in 1 mole. Then I'm going to multiply by 16 moles of CO2 for every 2 moles of C8H18. So I'm going to get that there are 57.483 moles of CO2 produced in this reaction. Then I'm going to go ahead and plug this into my PV equals nRT, which has been rearranged to solve for V. So nRT over V. Oops, P. So the volume is going to be equal to the moles of CO2, which is 57.483 moles, multiplied by the ideal gas constant of 0.08206 liters, atmospheres, moles, Kelvin, multiplied by the temperature of 291.4 Kelvin, divided by, in this case, the pressure of 0.928 atmospheres. And so when you plug this into your calculator, you would get 1480.9 liters. Based on our calculations, we should only have 3 significant figures. So once we use significant figures, the volume of this situation is 1,480 liters, or 1.48 times 10 to the third liters. Both of these are correct. So we can now use the ideal gas law or any of the relationships to understand how a gas functions under ideal conditions. And so we can look at those in a variety of different ways, and we can easily determine how it behaves using the ideal gas law of PV equals nRT.